Welcome. I hope you're having a great day. I'm Jesai Tarun from Indus International School, grade 11. I'm really excited to talk about. Welcome. I hope you're having a great day. I'm Jesai Tarun from Indus International School, grade 11. I hope you don't mind my camera causing my face to get stretched there. I can't change that. So I'm really excited to talk about my physics problem. It's problem number 10, magnetic gear. This problem tells us to take identical fidget spinners and attach neodymium magnets to their ends. When we place them side by side on a plane and rotate one spinner, the remaining one will rotate only due to the magnetic field. I conducted this experiment, and the investigation was intriguing indeed. I'd like to share both my investigation and explanation of the phenomenon in the coming minutes. Now, the first thing before we get started is to verify or is to explain what moment of force is. So, moment of force, also known as torque, as everybody knows, is the rotational effect of a force acting on an object about an axis. And we measure it in Newton meters. And it's measured as the cross product of the force and the perpendicular distance between the line of action of force and the axis of rotation. Now, if that sounded very jargony, here we have a nice diagram of it. Here, the moment of force acting on this would be the moment of force tau would be r, the red vector, and also the dark blue force vector, right? And the important thing to keep in mind is that we only consider perpendicular component of the force vector, right? So we'd have to do f sine theta to get the perpendicular component of the force vector to the r vector. So this is a very nicely written way of the entire definition. R crossed with the f vector, and that will give you r x sine theta, where these are the magnitudes of the respective vectors. So this is important for us to get into our experiment here. This is my experimental setup. So one thing to keep in mind is that the two spinners' centers will always be in a straight line relative to each other. We just have to make sure that the distance between the magnets will be as little as possible. So I have ensured that they are less than or at a millimeter apart from each other in all my tests. So this is the experimental setup in real life. I will get it to the camera. So I found these powerful neodymium magnets, like it's insanely powerful, and it allowed me to get a really good idea of what happens. So this is the magnetic field line of my magnet for reference. At one side of the magnet, let me try demonstrating that. One side of the magnet will always be the north side, and the other side will be the south pole, as you can see here. So in my experimental setup, I positioned them in such a way that the north pole will always be facing outward, which means that for both the spinners. So which means that as the magnets come close together during their rotation, there will be repulsion. Now, if you arrange them in such a way that they will attract each other as they come closer, you arrange everything with the north pole facing outward here and maybe the south pole facing outward here, you'll have very similar results to what I'm going to explain with the repulsion as a focus. So moving on, a very important thing to keep in mind. Now, as the magnet, let's imagine that we want the bottom green one to rotate clockwise, and we want the top black spinner to rotate counterclockwise. When this green spinner reaches this position, this black spinner's magnet could be at any position along this dotted line, and this is because the motion is not going to be uniform across the spinners. The frequency of rotation of each spinner will be a little bit different due to my initial torque application for each spinner being a little different. And also, there are slight different ball bearing friction levels between both the spinners, which will cause deceleration in a different way. Again, adding to the fact that their frequency of rotation was not going to be the same. And finally, even the initial position of the magnets before I instigated their rotation, that will also affect where they'll end up being, right? So at the end of the day, we can be sure that as this magnet comes here to get contact with the other spinner, this could be in any of these positions, and we're going to explore them in some certain cases. So the first case is where they meet in this same position as I showed you here. So again, assume that the bottom one is rotating clockwise and the top one is rotating counterclockwise. If they happen to meet in this position, we can see that due to the repulsion, the component of the force vector is going to be like this. And that's going to cause the torque to resist the motion, right? As you can see, the motion is in the opposite direction of the torque for each case. So this is going to impede the rotation. Now let's see this in action. When this motion decrease is going to be a majority, we see this. As you can see, the green spinner is not being allowed to spin up due to that repulsion happening as a primary thing. It's quite evident. Here we have the repulsion happening as the main focus. Now, sometimes this could also happen. So let's say as this comes here, this top one ends up meeting as they both exit their rotation, right? So in this case, again, the bottom one is trying to rotate clockwise, the top one is trying to rotate counterclockwise, because only that allows for this gear-like situation, right? Now here, in this case, if they happen to meet in this position, the repulsion will actually allow their rotation to continue, right? The repulsion will cause these force vectors to move along a direction that does not resist their inherent rotation. So here, in this case, we see that the motion is not stopped. So if you want to actually try and demonstrate this, let me, for instance, try and keep one of the spinners constantly moving by applying torque to the other spinner. Both spinners are going to try and slow down because there's a lot of friction in the ball bearings and there's also air resistance. So as you can see in this example, I'm trying to keep the green spinner constantly rotating by periodically applying torque to the black spinner. And you can see that in this case, the green spinner is not being resisted by the black spinner. The black spinner is actually allowing the green spinner to increase its rotation or continue its rotation, right? As you can see, the green spinner just increased in speed. So here you can see that this is happening primarily compared to this. Also, I'd like to talk about another very interesting thing that can happen when motion is not being completely impeded, as in case 2. Here, as you watch the next clip I'm going to show you, you'll see that the green spinner slows down on its own, and at the same time, the black spinner will speed up. A few moments later, the opposite will happen. The cycle can go on. In this case, rotational energy is being transferred or shared between the two spinners. They end up acting like one system under ideal magnet contact timing conditions. That's this clip. So as you can see right now, the black one is moving slowly. Now suddenly the black one moves fast and the green one will move slowly. Now again the opposite happened. And now the black one speeds up and the green one slows down. As you can see, that's constantly cycling between the black one speeding up, green one slowing down, and then the green one speeding up, black one slowing down. So again, this is just a very interesting thing that I found to be interesting at least. So also there's this other case where if they happen to meet exactly here, like this, in this case, in this position specifically, there's going to be no change to the net torque. Because as you can see, the force vectors are going to be, intuitively, the force vectors are going to be opposing each other. And also using the formula, we see that theta is 0 in RF sine theta. So tau is actually 0, right? Now, here are some interesting variables and things that I would like to investigate further. Now, the first thing is that change in the shape and orientation of the magnets will cause the north and south pole positions and, in turn, the magnetic field lines shape to change. This will obviously affect their interaction, right? And that's one question. And the second thing that I would like to look into is it possible to predict or see any pattern here? Now, I investigated this very thoroughly using slow motion cameras and the like. But what I found is that even as good as my fidget spinner is, the friction in the ball bearing makes their motion stop so quickly that you can't really try and predict many patterns out of it. You need to constantly keep putting an additional torque to keep them moving. And that's going to break any pattern that you would have seen, right? Now, one interesting thing is that I actually tried addressing my first question. So I tried my same experimental setup with a different set of magnets. Now, these magnets have this peculiar shape, and they have a very interesting field diagram. But I found the exact same three broad cases happening. Case 1, case 2, case 1, and even case 3, as you can see. So really the magnets have not made as much of an impact. The shape of the magnets have not made as much of an impact as I would have imagined, although I would like to investigate this further. Now, finally, also the strength of the magnet will affect the interaction, right? And also the distance between them. So these are things that I have control to keep as high as possible with the resources that I have. And across all the tests I've done, they've been controlled to be the same. Thank you so much for your time. And I truly say this from the bottom of my heart. Thank you, the INYPT team, for conducting this. It's not every day that you get to showcase your love for physics in this fun way. And this is one such opportunity that I will forever cherish. Have a great day.